semiconductor that is a carbon based material, the graphene or a graphite, uh, 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 then the graphene oxide, the carbon nanotube, or C3N4. These are metal free, eco friendly, and low cost material. Here in our talk, we'll be using some of the material that is a metal oxide based material and carbon based material, and we try to modify the property of this different material. Now this is the basically band gap and the band edge potential of the different semiconductors. If you take an example of a TiO2, it is a anatase TiO2. It has a the valence band position. This is the valence band position. This is the valence conduction band position, and this is the scale. In order to act as a catalyst, one should have the oxidation potential in between the hydroxyl radical and superoxide ion, and this band edge potential, it is important. Band gap potential, again it is important when it is used for the photocatalytic application. Then what is ideal semiconductor photocatalyst? It should be reasonably photocatalytic activity. It should have a low cost. It should have a appreciable band gap position. It should be activated by sunlight, since the sunlight contain more component of visible and IR and less component of UV. It should be chemically and biologically inert. That means it should be stable into the atmosphere. It should be non-toxic, and it should be environmental and economically acceptable. Now, if you look at the TiO2 as a ideal photocatalyst, there are some advantages with the TiO2. There are some limitations with the TiO2. TiO2, it is chemically and biologically inert. It is a protostable. It is a biocompatible. It is non-toxic. It has a moderate cost involved, but the limitation is that it has a low quantum efficiency. It is a UV active, particularly anatase. This TiO2, it is present in a 3 different allotropic form: anatase, rutile, and bruchite. And highly used is the anatase, which is a stable allotrope form of this TiO2, which is a band gap of this anatase TiO2. It is 3.02, and which is a UV active, and because of this UV active, most of the solar radiation, it cannot be used, and it has a low surface area. So the different strategy we fixed to enhance the photoactivity by modification of their structure, band structure. The enhancement, this modification that can be done by enhancement of the surface area by synthesizing the nano size particle. If the particle, it is smaller particle, the surface area that is less. So we try to develop a material which will be having high surface area, smaller size. Then multiple doping can be reduced the band gap. We know the band gap, it consists of a valence band, conduction band, and if it is doped with a metallic semiconductor, there is a introduction of energy level below the conduction band, and there is a reduction in the band gap energy. Then if we doped it with a non-metallic element, then there is a insertion of the energy level above the valence band, and the width of the valence band edge, it will be enhanced, and there will be again a variation in the band gap position. Improve the lifetime of a photo generated charge carrier by making composite or a copolymer, and heterostructure shows enhanced property as a result of synergetic effect. Now we have seen that earlier, the TiO2, it is a anatase. It is a basically UV active, and band gap is 3.02. Anatase TiO2, it is a UV active. How to modify this TiO2 UV active to the visible range? We try to multi-dope this TiO2 with metallic and non-metallic dopant and form the cerium nitrogen sulfur doped TiO2. This is a synthesis of the TiO2, simple TiO2, anatase TiO2, Ti metal dissolved into 4 normal HCl solution, and It is there is addition of ethylene glycol, and then again it is reflex for 100 degrees centigrade for 10 minutes. There is a more addition of ethylene glycol along with the urea, and there is a formation of hydroxide. Then it is washed clean and it is dried at oven and it is calcinated 500 degrees centigrade in order to get TiO2. This gives the TiO2, which is a anatase TiO2. Now, in order to get the cerium doped TiO2, cerium solution, cerium ammonium nitrate solution, it is added into along with the Ti solution. This ceria, it is added with the different percentage, atomic percentage from 0.6 atomic percent to the 2 atomic percent, differ for synthesis of different samples. And there is an addition of thiourea. This TiO2 and thiourea, it is 1:4 proportion, and it is grind, it is mixed properly, and then it is calcinated at 400 degrees centigrade to get the cerium nitrogen sulfur doped TiO2. Initially, ceria doped TiO2 it is obtained. Ceria doped TiO2 it is mixed with thiourea, and by adopting the procedure, one gets a ceria nitrogen doped TiO2. This is the ceria doped TiO2. This is the TiO2 without dopant, the powder XRD pattern of the TiO2. This is nitrogen sulfur doped TiO2, ceria doped TiO2 0.6 atomic percent, ceria 1% atomic percent TiO2, and ceria 0.6% nitrogen sulfur doped TiO2. All are crystalline, and this is an anodized phase, which shows the crystallite size of 14 to 16 nanometer, and there is no phase due to ceria which is observed in powder XRD pattern. This may be on the surface. There is no formation of any cerium oxide. There is no any peak corresponding to the cerium oxide. The crystallite size of this different TiO2 catalyst which is developed. This is the average crystallite size. The average crystallite size is less for the ceria 0.6% NsTiO2 dope TiO2, and again surface area that is increased. This is a P25. P25 it is a commercial TiO2 which consists of a 25% anatase and 28%, sorry, it is a 75%, it is wrongly, it is written, it is 78, 28, it is a 75. And the surface area for this commercial TiO2 it is 50. So this developed TiO2 it shows the higher surface area as well as the average crystallite size, lower crystallite size, and that is going to affect for a photocatalytic activity. This is a TAME image which shows the similar kind of image for the, this is for TiO2 and this is for ceria nitrogen sulfur dope TiO2. Average crystallite size it is around, this is 10 to 15 nanometer, and it is more or less same for TiO2 as well as for multi-dope TiO2. There is no much changes which is observed in a TAME analysis. Now this is the, in order to see the, okay, this is the XPS spectra which shows the presence of the different element and the chemical state of that particular element. It shows the presence of TiO2 in a TiO form. This is a TiO4 form, oxidation state 4, and ceria it is present in oxidation state 3 and oxidation state 4. Other than that, there is a presence of the other element, sulfur, oxygen, and nitrogen. Now, this is the effect of doping on band gap of a TiO2. This different TiO2 samples that we synthesize, TiO2, pure ceria 0.6% TiO2, nitrogen sulfur TiO2, and ceria 0.6% and nitrogen sulfur doped TiO2. This is the TiO2, this is the anatase TiO2, and there is an enhancement in the basically shift band gap. Band gap it is reduced, and visible light absorption, that is an enhancement in the visible light absorption for this multi-dope TiO2. And this multi-dope TiO2 absorption is maybe due to the doping, introduction of energy level of a metallic energy level, non-metallic energy level in the band, and there is an enhancement, there is a reduction in the band gap of the TiO2. This is the PL spectrum, photoluminescence. Photoluminescence, it shows the for a NSTiO2 and Syria dope NSTiO2, there is a broad peak that is observed, broadness, and it is shifting towards the higher wavelength. And this is a fluorescence lifetime. This is the intensity. We cannot conclude basically the lifetime based on the intensity because of the nature of the powder. Basically, PL spectra depends upon the intensity, depends on the powder sample, and this is the lifetime of a sample. And this is Syria doped 0.6% nitrogen sulfur TiO2. It shows the maximum lifetime, more lifetime. As we see earlier, basically, once the photo semiconductor it is exposed to the light, there is a generation of electron and hole. Electron and hole, they recombine very fast. We have to enlarge that lifespan. They recombine, recombination that has to be reduced. So by this process, the recombination that has been enhanced by multidoping. Now this is the reactor we generated in the laboratory in order to study the photodegradation of the different pollutant. Here we use the different pollutant, dyes as one of the pollutant. This is a reactor. We generated the light which is equivalent to the solar light, which is having the flux of 500 to 50,000 to 55,000 lux. And the photocatalyst along with the pollutant solution, it is taken to this reactor, it is stirred, it is exposed with the light for certain duration. With respect to time, the liquid it is removed, there is a separation of the catalyst, and the analysis it is performed by the spectrophotometer. This catalyst it is studied for the photocatalytic purpose using this methyl orange as a dye. This is an anionic dye which is absorbed at 463 nanometer, and this is the photocatalytic activity using different this catalyst, developed catalyst. This is for TiO2 using TiO2. This is using Syria 0.3% TiO2, Syria 1%, Syria 0.6%, and Syria 0.6%. That gives the better activity compared to the other TiO2 sample. Then the 0.6% TiO2, 6% Syria TiO2, it is doped with the NS, and this is the activity again compared with the other samples. This is a P25, which is a commercial P25. It is used as a commercial catalyst, commercial TiO2 for various application. And this P25, it has a lower band gap, lower efficiency compared to that of a cerium 0.6% NSTiO2. NSTiO2, again, it has a less efficiency, Syria 0.6% and TiO2, and this is the blank experiment which is performed without catalyst. This is the recyclability results. The recyclability of the catalyst that is performed, same catalyst, it is used several times after completion of the cycle. It is removed, it is washed, cleaned, dried, and again it is reused. And for several cycles it is used, and there is a marginal decrease in the efficiency, degradation efficiency of the dyes. Not much decrease in the efficiency, it is a marginal decrease in the efficiency. Then in order to know the species involved in the degradation process, we have done the quenching experiments. Different quenchers, these are used, isopropanol, benzoquinone, then ammonium oxalate. These are the different quenchers used. Isopropanol used for quenching the hydroxyl radical. Benzoquinone, that is used for the superoxide ion, and then ammonium oxalate, that is used for the quenching of the hole. And it is found that there is a decrease in the efficiency by use of these quenchers. This indicates that the degradation, it is because of all these species involved, hydroxyl radical, superoxide ion, hole are the major species involved in a photo degradation of the methyl orange. Now we try to explain this. We have a valence band, conduction band for a TiO2, and this is NS, this is the nitrogen sulfur, it is doped, there is a generation of energy level. Syria, it is doped, there is a generation of energy level below the conduction band, this is above the valence band. Widening of the band gap, valence band, it is occurred, and ultimately there is a reduction in the band gap of a formed TiO2, modified TiO2. So this is about the TiO2 modification using multi-doping. Ceria, nitrogen, sulfur, it is used as a multi-dopant. This is another system, TiO2, ZrO2. TiO2, again, we know it is a anatase TiO2, it is a UV active. And ZrO2, it is a higher band gap semiconductor, which has a band gap of 4.6, N type of a semiconductor. And surface acidity, it has a high. This is a not, it is not used as a, it is not a basically UV active, visible active. TiO2, it is a anatase, again it is not a visible active, this is not again a visible active. We tried to make a composite of it, TiO2 ZrO2, then we doped this composite with the bismuth and we found certain effect. This is the synthesis of TiO2 and ZrO2. TiO2, ZrO2, it is commercial. ZrO2 is used, taken in a propanol. Again, titanium isopropoxide, it is added along with the water. And this is form a ZrO2 TiO2 hydroxide. And on calcination, this gives a composite. In order to give the bismuth doped TiO2, at this stage, there is an addition of bismuth solution of bismuth nitrate. 1 atomic percent of bismuth nitrate is added, and the one can get the bismuth doped TiO2. It is the same process that is used. Now, in order to get the proper amount of ZrO2 required for a proper activity, we modify, we synthesize the different samples by varying the composition, TiO2 ZrO2 composition. And this is again the powder XRD pattern for the various catalysts that is developed. This is a ZrO2, this is TiO2, this is bismuth doped TiO2 and bismuth ZrO2. This is 90 TiO2 ZrO2 and 1% atomic weight percent bismuth doped 90 ZrO2 TiO2. This is the P25, which is again nothing but the commercial TiO2, consists of anatase and rutile. This is the anatase, and ZrO2 is a monoclinic, and in a composite it shows the monoclinic and zirconia and anatase TiO2. And ZrO2 TiO2, these are separate phase, and there is no phase corresponding to bismuth oxide. So again, bismuth, it is remain on the surface and it is act as a dopant. And this is the Raman spectra. It is again confirmed using this Raman spectra. This is the effect of bismuth doping. This is bismuth, it is doped. This effect of bismuth doping on the, this is the various basically catalyst, and this is a UV DRS spectra of the different compounds, different catalysts that is used. And this is the, this is blue one, it is the bismuth dope 90 TiO2 ZrO2. Again, there is an enhancement in the visible light absorption. And the P25, this is a P25, it is this is a P25, and other TiO2 ZrO2 samples, they are having the less absorption, less visible absorption, and there is an enhancement in the absorption, visible light absorption, due to formation of this composite and bismuth doping. Now this is the TEM image, which is a irregular shaped, and this is the HRTEM, which shows the interplanar distance, lattice fringes of ZrO2. This is a 0.026 nanometer lattice fringes, the interplanar distance for 002 plane, and for this TiO2 for 1002 plane, this is a 0.33 nanometer, that is the interplanar spacing. This is again the photoluminescence spectra and fluorescence lifetime for the different bismuth dope TiO2 and ZrO2. This is again a broadening of the peak that is observed because of the insertion of the making a composite and then addition of a dopant. There is a shift occurs towards the higher wavelength, and again there is an enhancement of a lifetime. If we this is obtained from a decay curve, fluorescence decay curve. For a bismuth dope TiO2 ZrO2, it is 8 at 4 nanosecond picosecond, and it is less for the other component. So there is an enhancement in the lifetime of a this catalyst, the composite bismuth dope composite. Then again the photo degradation experiment was performed using this all different ZrO2, TiO2 and different composite TiO2 ZrO2 composite, and this is a 90 TiO2 ZrO2. It shows the better efficiency towards the degradation of this malachite green. Malachite green, it is used as a pollutant in order to optimize basically the amount of the catalyst which can be used for degradation application. The loading, different loading was performed, and it is found that 0.35 is this loading, it gives the better activity, and we perform other experiments using this 0.35 loading of the catalyst. This is the degradation experiment again using different kinds of a catalyst using P25, commercial P25, and all the catalysts, comparing it with the 1% atomic percent bismuth dope TiO2, and this is the 1% atomic bismuth TiO2. This is a without dope bismuth. This is 90 TiO2. This is a without bismuth dope. This is with the bismuth dope, and this is a commercial P25. Again, this is a sample which is having better degradation efficiency compared to the P25. This is the degradation rate. It is very this is the degradation rate using this sample, and this is the degradation percentage, high degradation percentage, and the surface area. Surface area, it is 46 meters square per gram. We do the TOC, total organic carbon, in order to, it is converting into CO2 and water, and this carbon percentage, it is decreasing with respect to the sample. With the catalyst, along with the catalyst, the dye, it is exposed to the light. With respect to time, the sample, it is taken and it is analyzed by TOC for carbon estimation, and TOC carbon, it is decreasing. So this indicates that it is converting into CO2. No more the carbon, it is left out in the sample. And this is again the quencher study that we perform using the different quenchers, the what you call the different quenchers like the benzoquinone, then ammonium oxalate, or the isopropanol, and this is the activation efficiency, it is decreased using the different quenchers. And this is hydroxyl radical, superoxide ion, and hole. This is the species which is responsible for the degradation. This is the recyclability experiment. The same catalyst, this is the optimized catalyst, that is 1% bismuth, 90 ZrO2 TiO2. It is used for the recyclability experiment, and this is the efficiency. There is no decrease in the efficiency after 4 cycle, and this is verified. The used catalyst, again, it is analyzed using the XRD, and we found there is no change phase structure. There is no change in the phases. Phases is intact. That indicates that the catalyst, it is a stable catalyst. So again, this is, we try to explain this, how there is a enhancement, decrease in the band gap, and how this catalyst that is going to work. This is a TiO2 valence band, conduction band, and due to this addition of bismuth, additional energy level, there is a formation of a surface state. There is a transfer of energy from this conduction band of TiO2 to the TiO2 ZrO2, and there is an enhancement in the lifetime, that is the of a for a charge carrier. Now these are the two system, which is a TiO2 based system, and this TiO2, which is an anodized TiO2, which is UV active, and we try to convert it, modify it into the visible active, and the photoactivity that is developed. It is studied using the degradation of the different dyes. Now this is another system which is Ag loaded Gc3 and 4. Silver oxide loaded Gc3 and 4. You know, the Gc3 and 4, it is a basically semiconducting conjugated polymer. It is a most stable allotrope form of a C3 and 4. There are different again allotrope forms like the alpha diamond Gc3 and 4, but the stability it is poor. It is a two-D layered structure, and trizene is trizene unit. It is the building block of this polymer, and it has a carbon nitrogen ratio. It is 3 to 4. Then this is a layered structure, 2D layered structure of the Gc3 and 4. This is a S-trizene unit, and trizene unit, this is a primary block for Gc3 and 4. So it has a lot of basically the functionalities. It has a hydrogen moiety, Lewis base, and the again the different kinds of the functionalities. So what is the advantage and disadvantage challenges of this Gc3 and 4? Basically, advantage is that Gc3 and 4, it is a visible active. It has a band gap of 2.8 electron volt, which is a non-toxic. It is a 2D layered structure, metallic free. It is a low cost, easy fabrication. Surface functionalities are more, but the challenge is that it has a low surface area, marginal optical absorption in visible region. It has a uh, fast charge recombination, and the charge carrier mobility. It has a low charge mobility carrier. Now we try to synthesize this AgO loaded Gc3 and 4 microsphere. The 10 milligram of this melamine dissolved into 100 ml water along with the 5 ml of HCl. Then tetraethylene orthosilicates that is added along with the AgNO3, then ammonia. Then there is a precipitation is obtained, and this precipitate it is calcinated to get this melamine Ag uh, tetraethyl this is silicates as a complex, and this is treated with ammonium hydrogen difluoride for 12 hours to remove the silica present in it, and there is a we obtained this is AgO Gc3 and 4. Ag loaded Ag loaded Gc3 and 4. This is the again powder XRD pattern for Gc3 and 4. This is Gc3 and 4 XRD pattern, and this is at 27 around 27.5 of 2 theta degree. It shows the peak corresponding to the aromatic trizene interlayer stacking, and these are the all the peaks. This is for a composite AgO loaded Gc3 and 4, which shows the peak of this Gc3 and 4 along with the AgO and Ag. Then this is the FTIR spectra, which shows the presence of carbon nitrogen stretching as well as the carbon nitrogen which is present. This is in the Gc3 and 4. The similar kind of peak it is seen again in the composite. This is a morphology by the same picture, same photographs. It is a microsphere. It shows the microsphere structure, and this microsphere size it is around 3 to 15 nanometer. And this is the elemental mapping. It shows the presence of different element AgCNO as element. This is a tame photograph which is showing the presence of Ag on AgO and Gc3 and 4. This is a SAD pattern which is again showing the AgO, and this is the HR time which shows the lattice fringes of AgO of plane 002, which is 0.26 nanometer, and for Ag the dispacing for this 200 plane it is 0.20 nanometer. So there is a presence of the AgO and Gc3 and 4 in the composite, which is confirmed from the TAME, HR TAME and the SRD pattern. Again, XPS spectra it is taken and it shows the what you call the uh, elements present and oxidation state of the different element. Ag it is present in a +2 oxidation state, as well as Ag it is present in a 0 oxidation state, metallic state, and other element it is present the oxygen, sulfur, and carbon. Then the optical characterization, we have taken the DRS spectrum, UV DRS spectra, and this is a Kubel-Kammung plot. And this is a UV DRS spectra. This shows there is a shift, red shift. It is observed for a UV DRS spectra, and the band gap energy it is less compared to the GIS-3 and 4. This is for GIS-3 and 4 band gap energy is 2.76. And band gap energy for the composite Ag overloaded C3 and 4 it is 2.48. This may be due to the presence of AGO. AGO it is a low band gap 1.47 electron volt, and AGE which shows the what you call the surface plasmon resonance, metallic shows the surface plasmon resonance. This is the electrochemical and thermal study is performed for this sample, and this is the electrochemical impedance spectroscopic. This is a Nyquist plot, and this shows the arc. It is a lower, which indicates that this indicates the impedance, lower impedance, transfer of lower impedance, and the lifetime it is more. This is again, this is showing the cyclic voltammogram, and the cyclovoltammogram it is the capacity, larger capacity area for this AG composite, AGO composite compared to the C3 and 4. And this is a galvanic charge discharge, and the charging time, discharging time for the composite it is more compared to just 3 and 4. This indicates the supercapacitive property of this composite. Then this is again TG and DTG, which shows the stability of a material. The photoactivity of these different catalysts, again, it is performed using AV7, which is an anionic dye, acid violet 7 as an anionic dye. And this is the degradation experiments. It is performed, and this is a highest degradation efficiency for 10% of 10 atomic percent of the AGO loaded GIS-3 and 4. This is the 1%, 2%. This is the loaded AGO loaded on GIS-3 and 4, and this shows the maximum efficiency. In order to get again the proper amount of the catalyst used for degradation, this is a loading experiment is performed, and in order to see the effect of pH on the degradation, the degradation is performed at the different pH, and this is the experimental result, and it is found that it shows 10% AGO, it shows the maximum degradation efficiency. Again, recyclability is very important for a catalyst when it is used, and the various experiment it is performed. After each experiment, the catalyst was separated, it is washed clean and again dried, and again it is reused for another cycle. So in this fashion, the 5 cycle, the same catalyst that was used, and the XRD pattern, powder XRD, again it is taken, and it is found that again there is no change in the phase of the material. The phase it is intact. AG it is not, again it is AG, it is not a leaching. We analyze this with the ICP, and it is found that there is no AG in the solution. In order to study basically the degradation, the product, we do the degradation. Whether there is a degradation, what are the different degraded product obtained. In order to analyze the degraded product, it is analyzed by this is by the electrochemical ionization mass spectrometry, and this is for the without any exposure of a light for a anionic dye which shows the anionic dye AV7. This is the spectra. This is because of the mass spectra. This is because of the anionic dye AV7. After 10 minutes, this shows the degradation of a component, and this 527 peak, the intensity it is reduced. This peaks it is enhancing, and this peaks it is because of the dihydroxylate naphthalene. Again, after 20 minutes, this higher weight peaks, it is further reducing, and it is coming to the phenolic derivatives. This is 179 mass spectrum peak, that is corresponding to the lower derivative. So degradation, it is occurring with respect to time. This is indicative of, and we have seen that earlier there is the measurement by TOC. Then what are the product? We analyze by the product, and this is the peak. This is for a anionic AV7, and this is the compound which is formed after 10 minutes. This is hydroxylation. After hydroxylation, this is a dihydroxylate naphthalene after 10 minutes. After hydroxylation, it gives again a different kinds of a compound, maybe phenyl derivatives. And further, it gives a N-phenylamine and 4-methylene, 4-pentone 1. And at the end, there is a conversion into CO2 and water. Again, in order to study the quenchers, what are the different species involved in a degradation? Different quenchers, it is used ammonium oxalate, isopropanol, benzoquinone, which suppress the whole or a superoxide ion or the hydroxyl radical, and this is with the without quenchers, and these are all with the quenchers, and this is the efficiency, it is reduced without with the quenchers. So it indicates that this is a hydroxide ion, hydroxyl ion, oxygen and superoxide ion. These are the species involved in a degradation. We propose this is a mechanism. Basically, this is a C3N4, this is a AGO, and this is a AGO, it is loaded on Gc3N4. The band gap of Gc3N4, it is 2.72 electron volt. AGO, it is 1.12, and the valence conduction band of this Gc3N4, it is lower than the conduction band of a AGO. There is a transfer of electron on the absorption of a visible light, and this electron, it is again transferred to the AG, and hence there is a enhancement of a lifetime. This is, we propose the various reactions, how the degradation that can be performed. This is when this Gc3N4 exposed to the visible light, there is a formation of electron and hole, and this electron and hole, there is a, at the end there is a generation of hydroxyl hydroxide radical, which is responsible for the degradation. And from the quenching experiment that we have seen, there is a formation of hydroxyl radical, hole, and what you called the superoxide ion are the species which is responsible for the degradation of the experiment. This degradation basically results, we compared it with the different reported values reported in the literature. It is compared, and it is reasonably, it is better. The sample compound form, it shows the better activity. This is again which is used for the microbial activity. The microbial activity, again the catalyst it is taken, then the what you called the E. coli bacteria, it is added, and with respect to time, the population that has been evaluated by optical microscope, and this is the various images of a optical microscope, and this is a catalyst dose that is used, and as the dose is increasing, the death rate of a E. coli, it is increasing. And this is the blank experiment. This is using the light, and this is using the without catalyst, and this indicates that this is AGO GIS3 and 4 that can inhibit the bacterial growth, the E. coli bacterial growth. This is again with the various percentage of AGO loading effect on the growth of the bacteria. And this is the same image after degradation, after the basically reduction in the population of a bacteria. We have taken the same. Before exposure of a light, this is a original spectra before irradiation of a light, and this is after irradiation of light. This shows the killing, the rupture of a cell, bacterial cell. This image it is showing, and again with different quenchers we have seen the quenching effect. The quenching, this is without quenchers, and by addition of this sodium oxalate, which suppress the whole isopropyl alcohol, which suppress the hydroxyl radical. This indicates this is hydroxyl radical, and whole they are the species responsible for killing the cells, damaging the cells of a E. coli bacteria. Now this is the another system, one system that is a composite system that we have formed along with the C3N4. This is a phenyl grafted G3N4. Phenyl it is grafted. That is a earlier. It is a composite sample. It can say it is a homogeneous. We can say it is a homogeneous formation. So this is the uh, scheme for synthesis of phenyl grafted Gis3N4, phenyl urea. It is taken, it gives a phenyl substituted biurate, and then the cyanuric acid it is formed. There is addition of melamine, and at the end it gives a phenyl grafted Gis3N4. This is a optical spectrum and functional characterization. This is again a PXRD pattern for the pristine Gis3N4 and phenyl grafted Gis3N4. This shows again peak at around 27 degree centigrade for 002 plane for the trizine ring, aromatic trizine layered structure, which is appeared again in a phenyl grafted Gis3N4. But there is a reduction in the crystallinity. It is become a more amorphous, the broadening of the peak that is observed. This is a UVDRS, and which shows the more visible light absorption for a phenyl grafted Gis3N4 compared to the pristine Gis3N4. And this is again a Kubel-Kammung plot, which gives the band gap of 1.96 electron volt for phenyl grafted Gis3N4 compared to the Gis3N4. This is the IR spectra, which shows the CH, CN and C double bond end stretching in both the samples. And this is the solid state NMR spectra of the Gis3N4 and the phenyl grafted Gis3N4. And this phenyl grafted Gis3N4, there is a slight shift in the phenyl grafted Gis3N4. If you extended peak, it is, if you see, there is a slight shift in the phenyl grafted Gis3N4 in the C3 NMR spectrum. It is because of the grafting occur on the this is a Gis3N4. XPS spectra in order to study the chemical state and elements present in the sample. This is for Gis3N4. Amount of carbon nitrogen is 42%, and carbon nitrogen percentage is 0.77. But in phenyl grafted Gis3N4 phenyl, there is increase in the carbon percentage, and there is a decrease in the carbon percentage. Carbon nitrogen ratio it is 0.84. So this is clearly seen here. It shows the clearly seen that area there is a grafting that is occur, that indicating the grafting. This is the surface spectrum of Gis3N4 phenyl grafted Gis3N4, and shows the presence of nitrogen, carbon, and their areas, different areas. So this is the again Fe same image of the Gis3N4 and phenyl grafted Gis3N4. This is a it shows the similar kind of a spectrum, only there is a difference in the carbon nitrogen in a the SAD pattern. This is a HR tame, which shows this is the tame image, which shows just like a transparent sheet, and this is showing rolling self-like appearance, rolling like kind of appearance. This is a HR tame, which shows the flattest ranges of Gis3N4 of 230 plane of 0.32 nanometer, and for this is For the phenyl grafted GC3N4, it is for 002 plane, it is 0.33. There is an increase in the lattice despacing after grafting, and this is again the uh, SAT pattern. This is a ring structure, and this is little amorphous kind of a structure. Concentric ring here, and this is a amorphous kind of a structure. It is observed.
పొద్దునంతా కూర్చొని బతక నిలబొట్టి సాయంత్రం మీటింగ్ ఏంటి?
This is let me see. This is okay. This is the again nitrogen isotherm, adsorption isotherm, desorption adsorption isotherm, in order to calculate the pore size distribution and surface area. The surface area for GC3N4, it is hardly 9.55 gram per centimeter square. This is for 94%. There is a large enhancement in the surface area after grafting, phenyl grafting. And this is the pore size distribution. The pore size, this is shows the presence of the pore 0.5 to 4 nanometer in size, and again it is similar. There is no much difference in the pore, but the amount of pore that may be enhanced, and because of that there may be increase in the surface area of a phenyl grafted GC3N4. Now we have used this GC3N4, phenyl grafted GC3N4, for the CO2 reduction, and this is the experiment it is performed. This is the catalyst along with the DMF, triethylamine, and water. It is taken in this different ratio. CO2 it is taken inside, and then it is exposed with the light. It is a 20-watt white light LED for 24 hours, and the sample it is taken using a syringe, and it is analyzed with GC, FID, and CD, TCD, and this is analyzed using the GC, and it is found that this is the result. There is this is for methane. These are the different catalysts, and the amount of methane generated using this phenyl 100 GC3N4, it is highest. But for methyl formation, the 20 GC3N4, it gives the better methyl formation, as well as this formic acid formation, it is better by this phenyl GC3N4. So there is a generation of the different product. When this CO2 it is exposed with the light, CO2 it is converted into the different value added product, the methane, then the formic acid, the methanol. We try to explain using this basically mechanism. This is a basically limited study of this CO2 photo reduction that is reported so far. We propose a possible reaction pathway for the formation of methane, formaldehyde, and methanol on the surface of GC3N4. When this GC3N4, the phenyl grafted GC3N4, this is a redox potential of 1.01 electron volt, suitable for the reduction of a CO2. On irradiation of this visible light, this is on irradiation of visible light, it generates the electron and hole, and the conduction band electron, hole in a valence band, and the surface adsorbs CO2. It is react with the electron. This is reacting and generating the interact. Basically, the GC3N4, it has a nitrogen carbon. It has a lone pair of electron, and there is adsorption of CO2, and there is a reduction. It is performed, and the reduction potential for CO2 to formic acid, it is less negative compared to the redox potential of this phenyl grafted GC3N4, and hence there is a formation of these different kinds of a product. Similarly, the oxidation potential, this is the oxidation potential for phenyl GC3N4, which is 1.65 electron volt. and is sufficient more positive than the oxidation potential of the hydrogen and oxygen formation. It may leads to cleavage of the carbon oxygen and the formation of a carbon hydrogen bond. So there is a degradation of CO2 and formation of a value added product using this phenyl grafted GC3N4. Again, the photocatalytic activity we have performed using the same catalyst, phenyl grafted GC3N4 of different percentage using rhodamine B as a catalyst, which is a cationic dye, and this is the dark experiment, this is the light, and this is phenyl 20 GC3N4. It shows the highest activity among the all other catalysts. Again, this is a quencher experiment in order to know the different the radicals involved in a degradation. These are the radicals which are involved in a degradation, and this is a photoluminescence spectra and decay curve. This is the photoluminescence spectra of phenyl grafted GC3N4. It is for GC3N4, and you know the lifetime for a phenyl grafted GC3N4 is less, and for a C3N4, GC3N4, it is high. The when it is excited, generation of electron and hole, and it is recombined, and the recombination rate is high here. Recombination is reduced because of the phenyl grafting, which is an aromatic ring, which is there is a formation of mid-gap structure, and this is a again what you call the lifetime of the phenyl grafted GC3N4 and the GC3N4. This is recyclability experiment. Again, repeated cycle was performed, and the same catalyst was reused, and there is a marginal decrease in the photoactivity for degradation. And once it is getting heated for these temperature, again the activity it is again reappearing. It is coming. It is in same. This is the XRD pattern for recycled phenyl grafted GIS3 and 4, and this is for a fresh sample. There is no change. This is again the same picture, same image, and the same image. It is a similar kind of image. It is observed. This is indicating there is no much change in the structure after use of phenyl grafted GIS3 and 4 for phenyl degradation, for rhodamine B degradation, as well as for the CO2 reduction. This is the proposed mechanism for the degradation of a rhodamine B. When this light it is exposed, there is a formation of electron and hole. This is the electron. It can give the superoxide ion. The superoxide ion further reacting, it gives the hydroxyl radical, and this hydroxyl radical, which is responsible for the degradation of rhodamine B. So with this is the basically summary and conclusion. So we have seen so far the modification of a TiO2, modification of a GC3 and 4. TiO2, it is an anatase, which is a UV active. We try to multi-dope with the metallic dopant, non-metallic dopant, and brought the band gap to the lower value and UV visible region. And it is a the stability, it is a better stability. The in a second, we have seen there is a formation of a composite ZrO2 TiO2. ZrO2 it is anatase. TiO2 is anatase. ZrO2 it is a monoclinic, and it has a high band gap. Both are high band gap and brought the visible the absorption in a visible region by again enhancement is observed by doping with the bismuth. Then GC3 and 4, it is a carbon-based material. It has a lower efficiency towards the catalytic efficiency, and catalytic efficiency that has been enhanced by forming a composite with the AgAgO, and the other composite, that is a other where we can say the grafting, it is performed using phenyl grafting, and there is a enhancement in lifetime used for different application, for degradation of dye, for inhibition of the E. coli bacteria, then the conversion of CO2 into the useful product. So these are the various the catalyst, and that is the use. So we can say photocatalytic route can be considered to be a green process for energy and environmental remediation, and photocatalysis can play a vital role in a sustainable development. So I thanks the organizer for giving me the opportunity to present the work which is performed in my laboratory by different student, Dr. Vidyasagar. This is the work what I have presented. This is the work done by Dr. Vidyasagar, Dr. Sachin Google, and supported by Toshali. He is the present current student. My collaborator, Dr. Shashikala, then Dr. Ragumani, and I thank to the funding agency, UGC, BRNS, DST, MHRD, and I thanks to the organizer for giving me this opportunity. So thank you, Dr. Sonawane. I can let me see the questions. Hello,
Thank you very much,
Dr.
sir.
Sonawane, I'm visible. Am I audible?
Yes, sir. Thank you very much.
Okay, let me check the chat box for the questions.
Question started from Q.
Yes. So,
This question.
okay. I, okay. This is,
There is one question.
I think I have sent some, okay. There is, I think, no question, I think.
So this one question is there.
Huh?
If you see down, there is one question. Can we increase UV activity?
Uh, understand, okay. I sit here with this all. What is that question?
Can we increase UV activity, visible activity and recycling in battery application by reducing the size of TiO2 P25 without doping?
Can you repeat this question?
I will again post that question. I will again repost that question. Now that question is posted. If you see chat
Uh,
box.
at lowest, it is at the lowest.
Yeah, lowest.
Okay, okay. Can we increase UV activity, visible activity, and recycling in battery application for reducing the size TiO2 P25 without doping? See, activity that can be some modification definitely has to perform. For activity enhancement, TiO2 anatase it is a 3.02, rutile it is less 3.2, 2.8, and brucite. And P25 it is a basically commercial P25, and it is a combination of rutile and anatase. And if you definitely one has to modify, either you have to modify by doping, you have to modify the surface, maybe by reducing the size, enhancing the surface area, or you can modify the again TiO2 or P25 by making the composite. But anyway, but you have to modify it. Unless you modify, we cannot say the activity can be enhanced. Right, so modification it is important. So different methods it is used for modification, as we have seen. There is a modification by multi-doping, modification by making a composite, modification by again by grafting. So different methods that can be used for modification of a different material. I think I answered the question.
Sir, thank you very much for answering the question. And also, I am very much personally thankful to you because you have accepted our invitation and delivered two talks basically. This is a great thing. And dear participants, uh, time is now 3:48. Don't leave the session. Session will be on exactly sharply at 4 p.m. Professor Aniruddha B. Pandit, Professor A.B. Pandit, he is the Vice Chancellor of Institute of Chemical Technology, Matunga, Mumbai, will be joining with us for a valedictory session. And immediately after his guidance, at around 4:30 to 5 p.m., our examination will be started. So don't go anywhere. Please be online. Only you can take a break of 10 to 15 minutes and then rejoin. resit for this particular validatory session. Okay, so don't leave the session, be with the session, only take a tea break and just come back again. Thank you very much, sir. Sir, you also invited for that session. Please join at 4 p.m. sharp.
Ah, yeah, definitely, definitely. So thank you for invitation again. Oh, I will join for valedictory function. I will join.
Yes, sir. Yes, sir. Thank you very much. Thank you. Bye bye. Thank you. Just be there. Be there. Only just take a tea break, virtual tea break.
Ah, yeah, sure, sure, sure. Yeah. Ah, okay. Oh.
I'm liking it. Her name is there. Hand report, right?
Sir, am I audible to you?
Yes, you are very much.
Okay, your voice is also clear, sir. Namaskar.
Namaskar.
Sir, sir, it is fine. How are you, sir?
I'm fine. Everything is fine. I think it's reception is very good. No issues.
Okay, okay, okay. So, sir, we will join sharply at 4 o'clock.
Okay, will do.
Okay.
हाँ ठीक है चल ओके Nilesh, well, I just have to address one validatory function. I'll get
Respected sir, dear participants, sir, shall I start?
Please do. Please go ahead.
Dear participants, uh, we have completed our AICT sponsored Atal Faculty Development Program, and the time come that let us have a validity session of this particular Atal Faculty Development Program, which is sponsored by AICT. We have with us a very eminent specialist, scientist, and a great chemical engineer, Professor Aniruddha B. Pandit, sir. Sir was born on 7th December 1957 in Mumbai, Maharashtra. Sir is BTech, MTech, and PhD Chemical Engineering. And right now he is a Vice Chancellor of Institute of Chemical Technology, Mumbai, Matunga. As far as Sir's other contribution is concerned, that is something extraordinary. A lot of awards on Sir's credit. IST National Award for Outstanding Research. Then Professor R.A. Rajari Akshub Best Teacher Award. Sir is Fellow of Maharashtra Academy of Science and lot more. To read his biodata is something a very uh, hard job. Sir is a fellow member of IICHE. Sir has, to his credit, Handicap Awards for Excellence in Basic Research, Distinguished Alumnus Award, Institute of Technology, Banaras Hindu University, Distinguished Alumnus Award, University 2008, INSA Best Teacher Award, Vishwakarma Medical Medal of Indian National Science Academy 2015. Sir is Fellow of Maharashtra Academy of Science, Indian National Academy of Engineering, Indian Academy of Sciences, Indian National Science Academy, National Academy of Sciences, and as far as research is concerned, uh, Sir has published so many papers, but I will only read his citations. Sir's research paper citation is over 26,000. So over 36,000 research citation is a too, the big task basically, sir. You are really a god for chemical engineering. You are a god of chemical engineering. After M.M. Sharma, I will say, Professor M.M. Sharma, I will say, sir is a father of chemical engineers. Many books are there to his credit, many book chapters. Sir has guided 48 PhDs till date, 88 masters so far, more than 15 patents, and more than 400 publications uh, to Sir's credit. Sir has handled many administrative responsibilities, and he has a big contribution in all over India, I can say, all Indian institutions, wherever chemical engineering is there, he has contributed in developing the syllabus, he has contributed in selection of faculty, and so on. I welcome sir to this validity session, and I request you to address the participants. Let me just describe, mention here is that this particular faculty program which AICT has sponsored under Atal scheme, and this has been started on 24th of August to this date, 28th of August, and various eminent speaker. Ashok Kumar Muthipandian, sir, who is the Vice Chancellor of Melbourne University, he was chief guest for inaugural session, and also he has delivered his talk. And other experts were from NITs, IITs, and CSTR laboratories. They have delivered various experts talks, and the theme of this particular event was the nanotechnology for sustainable development and green process synthesis. Sir, we want your guidance and uh, uh, for the participants, please.
Thank you, Shriram. And thank you for a very kind introduction, a very generous introduction, that
Sir, your
too.
voice is not audible. Your voice is not audible.
Let me just then use. Is it audible now?
Yes, sir, it is audible.
Yeah, thank you. I said thank you for such a generous introduction, Sriram.
Thank you very much.
And I think it's been very kind of you to ask me to address this 125 participants. It's outstanding. I had a look at the general program and the kind of speakers which you have gathered for this 5 day, 14 session faculty development program has been fantastic and amazing. So I wish I had attended few of these, and I see that you have been able to cover a gamut of topics ranging from ultrasonic processing, green processing, nanoparticle synthesis, the usage of nanoparticles, water cleaning up, water purification, usage of nanoparticles as nanocatalysts. I mean, everyone I'm sure who had attended this faculty development program would have had something to learn from this particular 5 day session. Now, the theme which you correctly pointed out is green processing and green synthesis is extremely important. And I would go a step ahead that it is the first step which you need to undertake to ensure the sustainability of not only chemical engineering, but also the chemical engineering based operations. Because the sustainability issue and the sustainability goals which United Nations have defined are the key factors which everyone has to take into account when they are either learning or teaching their students. If you remember 25 years ago, maybe 30 years ago, there was no such subject as EVS, environmental sciences, at school level. But if you see now, is EVS is a core subject which is taught in every school. As a result of which, you find that the students who are graduating or who are coming out of school are environmentally much more aware as compared to what we were when we were of their age. Similarly, a sustainability issue, green processing, then sustainable manufacturing are going to be the key driving components of chemical engineering profession. Now, similar to what we started looking at in the initial stages as end of the pipe solutions, end of the pipe solutions are okay as a stopgap arrangement, but they cannot be sustainable themselves. As a result of which, to be able to address any problem in a sustainable manner, it is necessary for us to understand the basic science behind any of these applications or any of these technologies. And I'm sure due consideration must have been given when all these topics of nanoparticle synthesis, nanoparticle usage, ultrasonic sonochemistry, green processing, all these were discussed. And I see quite a few familiar speakers in that. Actually, I see Shri Umare, Naveen Shimpi was there, Admin Mungre was there, Labeswar was there, Dr. Sadhna Railu was there, Akola was there, and Shriram Sonawane himself. So I see many of these have been my collaborators, have interacted with them in the past, and it is quite laudable on their part that they have come together to assist Shriram in holding this particular faculty development program. Such faculty development programs are a key, at least in this particular period, as well as in a true sense, because this is the only way, in addition to reading each other's research publications, we come to know what are the thinking philosophies which everyone is following on the basis of which he or she himself is sustaining himself or herself in terms of research activity and the creation and dissemination of new knowledge. So, as I was mentioning about the sustainability issues which are there, similar to we initially starting now with kind of program which was just conducted, did offer many of the utilities of this green processing, but to be able to understand and think in terms of sustainable solution, it is mandatory and it is essential for us to start learning it from the school levels or from our undergraduate level. Every undergraduate subject in chemical engineering will find has a certain sustainability component, and that sustainability component needs to be enhanced. And at least the teacher who's teaching that particular subject needs to make student aware of the fact that are sensitized of the fact that the same activity cannot go on forever unless these activities are linked to the kind of resources which it utilizes, the kind of waste which it generates, the kind of influence it has on the environment and the surroundings. So sustainability for our own profession, chemical engineering profession itself needs to be looked at because the conventional chemical engineering teaching and modern chemical engineering teaching has gone through a significant change and this change is continuous. So addressing and conducting seminars or FDPs like this is going to make all the faculty aware of at least the existence or at least the opportunities which exist for each of them to further their own learning as well as how they can share their own learning as well as the created knowledge through research to disseminate it to their own students and thereby promoting the issues of sustainability, issues of green chemistry, and issues of sustainable manufacturing. So my sincere compliments to Shriram for thinking and conducting such a workshop or such a program, which has been extremely useful. And I'm sure he will conduct many such programs and with enthusiastic participation from all of you participants and faculties. My request to you use this as a prompt to each one of yourselves, and you also come up and start something locally and create and spread the information which you have learned or the knowledge which you have learned during this particular program so that the chain reaction continues and it propagates. All the very best for your future efforts. Thank you, Shriram, for inviting me to address you all. And I'll be more than happy to assist all efforts of you as well as your colleagues, all other participants, if they are interested in taking my assistance, my advice. I'm always available. Thank you very much, Shriram.
Sir, thank you very much for your blessings. Also, we are going to organize JN program after this pandemic situation is over. So you have to visit VNIT. So as per your guidance and suggestions,
I've already given a commitment to that. Yes.
so I will be continuing organizing such programs in future also. Thank you very much, sir. Thank you very much.
Thank you.
Okay. Dear participants, don't leave the meetings. Now the exam test will be posted and it will be start at sharply at 4:30 that you have to attend. So be online, don't leave the meeting so that if you have not done registration yet, please do the registration. Thank you very much. Thank you, very much, sir. Keep your blessings. Thank you.
Thank you. Shall I log off?
Yes, sir.
Yeah, thank you.
So come here now, our team. अपनी टीम आ जाओ. कहाँ है वो? ये क्लब वाले लॉन्च अभी कर रही है क्या?
नाही परत ती लॉन्च अजून नाही कसं एंडेड स्टेटस येत होतं ना किती झालं सर
34.
विचारून म्हणतो
So, dear participants, till now only few participants have registered for the test. Please quickly register so that we can start posting test sharply at 4:30. Even I have sent link via Telegram. If you see our Telegram group, those who have not registered for the test, please register so that you can post your answers. अभी कैसा करें?
मोबाइल मेरा लैपटॉप उसका खराब है मोबाइल में मोबाइल में वो रजिस्ट्रेशन आईडी वगैरह मांगता है उसको कैसे कर सकते हैं आता है वो रजिस्ट्रेशन आईडी रजिस्ट्रेशन उसको
कुछ भी नहीं है उसमें. All participants are requested to register for the exam. We have already sent link to your email and Telegram group.
सोनावणे सर ही मीटिंग सोडून एक्झामची मीटिंगला गेलेलं चालेल का?
हो ही मीटिंग सोडून तुम्ही एक्झामच्या मीटिंगला जा ना. यस.
ठीक थँक्यू सर.
See, you can leave this meeting and you can connect to the exam meeting. This meeting is over and exam link meeting will be on. So you can leave this meeting and join to the exam meeting. If there is any issue, you can leave this meeting and you can join exam meeting.